So we learned how to determine the molecular geometry for polarity. Okay? So right in the Lewis structure, determining the molecular geometry, that is all for polarity. Does everybody understand what polarity is? Yeah. No? Okay, so here it is. Polarity is a condition when the electrons in a covalent compound are shared unequally. So let's first start simple. Let's start with the covalent bonds that are polar. So let's just talk about polar bonds. So for example, let's say we have H and Cl bond. If you guys have your electronegativity chart still? If you have that out, use that. And we're going to use that a lot today. So what is the electronegativity value for hydrogen? 2.1. 2.1. And what is it for chlorine? 3.0. 3.0. Okay. So this is electronegativity. Who can tell me what electronegativity means? The ability of an atom to what?
Attract electrons.
Attract electrons during a chemical reaction. Okay? So chlorine wants to take these electrons a little bit more than the hydrogen, yeah? When the difference is greater than 0.4, then we say it's polar. Now, that's good, but sometimes what if it's 0.4? Is there still a difference? There still is a difference. That means, in general, it still could be polar, but we'll just keep it simple, okay? We'll just put a scale here. So if this is 0, 0.5 right here, and we'll just say 1 point, and I don't really like the upper one. I'll just stick with this one. Okay. If it is everything below 0.5, we say that it is a nonpolar bond. And if it is everything including 0.5 and above, this way, then we say it is a polar bond. Oh. Okay. And if what is, I kind of mentioned, but I didn't write it, the difference in electronegativity.
0.9.
In electronegativity. So if that difference is less than 0.5, then it's considered to be a nonpolar bond. If it's greater than 0.5 or equal to 0.5, then it is a polar bond. Are we good? And that's going to be our first step to determine whether the molecule or the compound is polar or not. Okay? Question?
Just for clarification, if it's exactly 0.5, it's
Polar. So this little bracket, that says it includes 0.5. And the parentheses, so this is just a math convention. Parentheses says it doesn't include it. Does that make sense? So yeah, anything 0.5 or greater is considered polar. And my notes say if it's greater than 1.9, then it's considered ionic. But can you guys tell if a compound is ionic just by looking at it? How do you tell? Couple different ways you can tell. If it's with a metal. If there's a metal in it, this is an ionic compound, and we're not going to call it a polar covalent compound. You with me? So that's why I'm not writing it here, because we could tell if it's ionic. What if it doesn't have a metal in it? Does it mean it's always a covalent compound? It doesn't. Okay? Well, what's an example? With a polyatomic ion ammonium in it, or hydrogen, like for acids. So if it's a compound that's made of ions, it is an ionic compound, period. No exceptions. And most cations are metals. There are a couple that are not. One's hydrogen, one's ammonium that we deal with in this class. And so you got to be familiar with those polyatomic ions. Good? All right, so is hydrogen chloride a polar bond or a nonpolar bond? Polar, because the difference between 3 and 2.1 equals 0.9, and that's right here, yeah? So it is a polar bond. Questions? So a lot of times we write this. Here's the bond. Whoops. Here's our bond. And we say, okay, here's the positive end, and it goes toward the negative end, because electrons tend to go toward chlorine, right? So it's like a tug of war between these, and chlorine wins because it's taken more. It has a higher electronegativity value. Good? So although they're sharing these electrons, chlorine says, okay, but I get most of them, right? I get them, I'm in charge of them, kind of like, right? Any questions how to determine if a bond is polar or not? Okay, next, if the bond is polar, we have to determine which side is partial positive, which side is partial negative, right? So, which side is partial negative?
The chlorine.
The chlorine. Why? Because it's more electronegative. More electronegative is partial negative. Make sense? Less electronegative is partial positive. And that's kind of why we draw the plus with the arrow going toward the negative, okay? Are we okay with that idea? Or maybe we should practice them a little bit, yeah? Okay, section 1 on your worksheet says to assign the electronegativity value. That's just looking it up on the chart and put it in. So if you want to do that, get practice to using your electronegativity chart, because you get this on the exam, right? This doesn't have to be a part of your little note card. Then you can. But let's go ahead and jump into section 2. It says, tell whether the following bonds are polar or nonpolar. If it's polar, show which side has an accumulation of negative, in other words, partial negative charge, or partial positive charge. Why do we call it partial negative and partial positive? Yeah, go ahead.
Because it's not all the way positive and all the way negative.
How do we know if it's all the way positive or all the way negative? If it's an ionic compound. So, for example, we have sodium and chloride. These are a full positive and a full negative, and they attract strongly. because of the electronegative, electrostatic force, okay? And that's why we call it partial positive and partial negative. Good? All right, so let's, we did the first one. Let's do the next one. In fact, let's jump down and do, I don't know, Cl and N. So look at our y'all have an electronegativity chart? Okay. Let's see, I don't know if I have any here. I don't even have a blank one, so. But anyway, you will get these, okay? So what's the electronegativity value for chlorine? We just did this one was 3, right? What is it for nitrogen? 3. So is this a polar bond or a nonpolar bond? Nonpolar, because the difference in electronegativity is 0. There's zero difference, so this is a nonpolar bond. Do we need to worry about the partial positive, partial negative here? No, because it's a nonpolar bond. Only if it's polar, okay? Let's try O and P. A bond between oxygen and phosphorus. What's the electronegativity value for oxygen? 3.5, and phosphorus is, what is it? 2.2. What's the difference? 1.3, so that is polar. So what do we need? Okay, which one's partial positive? Or actually, I like to say, which one's partial negative? Oxygen, because it's more electronegative, hence partial negative. Are we good? Makes the other one partial positive. So, a good way to look at this, you guys know what else is polar? Where have you heard that term before? North and South Pole? Yeah, like a magnet. So you have a magnet here. You have one side north, one side south. Oh. We can draw a distinct line between the North and the South Pole. We can draw a distinct line between the positive end and the negative end. Hence, it's polar. Are we good? It's kind of like a battery. So we have a battery here. We have the positive end of the battery, negative end of the battery. Batteries are also polar. Okay? Are we good? Or sometimes you call it polar opposites, right? Yeah. Good? Any questions on section 2? You want to try some of those a little bit? Practice doing them. While you're doing that, does anybody have a hard time seeing these molecules three-dimensionally? So there's a trigonal plane, it's all on the same plane, if you want to know. That's a tetrahedral. Okay. And that's basically it. That's linear if you want, right? Okay, good. But I will have these during the exam. Is that good for everybody? Do you like that? Okay. But either get those down or have them on your little card. Any questions on any of these? Would you like to do some more together? How you feeling? You're good, or you want to do more? Moving on?
Yeah.
Okay, you tell me if you need something. Okay, now let's determine if the molecule is polar or not. This one's a little bit more complex, more into it. So determining if molecule, when I say molecule, what am I talking about? A covalent compound, okay, is polar or nonpolar. Okay, so let's do some examples here. In fact, let's make some steps, right? That's a little bit better. So step one is we draw the Lewis structure. Any questions on that? Can you all do this in your sleep yet? So in other words, have you done it so many times you just start dreaming about it, right? Okay, well, you need to do it some more then. No. Okay. Step two is determine molecular geometry. Have we practiced this? Are we getting this down? Okay. Step three, determine if bonds are polar or nonpolar, and that's what we just learned. Any questions on that? So I'm not going to describe that each step again. We just did that, okay? So you find the difference in electronegativity. If there's a difference greater than 0.5, it's polar. If it's less, nonpolar. Should say greater than or equal to 0.5, right? And then the last step is, I should word this. If we can draw a straight line that separates, completely separates positive end from the negative end, then it's polar. If not, then it's nonpolar. We good? Who needs this screen up still? Okay. That's just the periodic table. Okay, we good? All right. Let's do an example. So we got carbon dioxide. And again, this is only worth doing for covalent compounds. If it's an ionic compound, we don't need to worry about this because there is a difference in positive and negative, right? So we just won't do this, okay? We won't call ionic compounds polar or nonpolar. Okay. So first step is to draw the Lewis structure. Can we all draw this? Yeah. How many valence electrons for carbon? 4. For oxygen is 6. Multiply that by 2 because there's a 2 right there. We add those together and we get 16 electrons. All right? Okay. Central atom is carbon. And we have 2 oxygens. How many electrons have we used so far? 4. So we have 12 left. Where do they go? Around oxygens to make it have an octet. We used all 12. We can't use any more. That's it. Now what do we do? Is carbon good? No. So what do we do?
Remove 2 pairs of the electrons from the oxygen and
Yeah.
make them double bonded to carbon.
There we go. So there it is. Okay? All right. What's our next step? We drew the Lewis structure. Now we do what? Molecular geometry. Yeah, yeah. So what is it?
Linear.
It's linear. There's only 2 regions, electron regions around the central atom. So it's linear. And I emailed everybody this sheet, right? The Vesper sheet. That's how we tell what the molecular geometry is. So if you wasn't here last time, use that. Or I will send out the video from last time. I didn't yet, but I'll get that. Try to do that tonight. We'll see if I can. Okay, so it's linear. Great. Now what do we do?
Determine if the bonds are polar.
Determine if the bonds are polar or nonpolar. So I got 2 carbon-oxygen bonds. Is this a polar bond or nonpolar? So we got a difference in 3.5 and 2.5. Definitely is a polar bond. Does that mean this is a polar molecule? No, it doesn't. So we have to further check, okay? So this is a polar bond. So what do we do if it's a polar bond? We write partial positive, partial negative. Which one's the partial negative, oxygen or carbon? Oxygen is partial negative because it's more electronegative. Y'all with me? And this it's the same bond, so just the same on that side. Can we draw a straight line that separates these? What if, when we drew our Lewis structure, we drew it like this? Is that okay to draw it like that? It's okay to draw the Lewis structure like that. But this is why we have to know what the molecular geometry is. We have to know what it looks like. Because if we drew this partial negative, partial positive, can we draw a line that separates it? Yes, we can. Don't fall into that trap, okay? You got to know what the shape is. That's why the second step is, what is the molecular geometry? Good? So is this a polar molecule or nonpolar? Nonpolar, we can't separate it. Are we good? We're good after we try like 10 more, right? Okay, let's do it. Okay, let's do CH4. Can you guys do electron or Lewis structure? Should I just draw it, or do I need to go through it? You tell me. Just draw it. Okay, there it is. What is the molecular geometry for this? Tetrahedral. Yep. So it looks like this. Yeah, I would actually draw it like this, so you can know if you could separate positive and negatives. Oops. Good? Okay. Well, is this bond polar or non-polar? Yeah, this is 2.5 and this is 2.4, 2.1. The difference is 0.4, non-polar. And I'm going to say something right here, and this will save you a lot of time if you know this. If a compound is carbon-hydrogen only, so it could have different numbers here, but if it's only a carbon-hydrogen compound, it's always non-polar. If all of the bonds are nonpolar, that makes this a nonpolar molecule. But if all of the bonds are polar, that does not make it a polar molecule. You with me? Maybe we should write that down. If all bonds are nonpolar, then molecule is also nonpolar. But the flip-flop is not true. Just like in that example with carbon dioxide. Had polar bonds, 0 nonpolar bonds, but it was a nonpolar molecule. So we have to do the line test. We good? Okay, let's do another one. NH3. There's the Lewis structure. So what's the molecular geometry? Somebody besides Aiden tell me. I'm just teasing. But can we do this? I'm just checking. What?
Is it a trigonal planar?
Not quite. Why isn't it trigonal planar? Let's count the regions. 1, 2, 3, 4. Remember, we got to count that lone pair. So there's one lone pair, and it's a 4 trigonal pyramid. That's right. Are we good? Okay. Well, thanks for participating. This is what helps you learn, guys. It really does. Okay, so we have nitrogen here. Let's draw it. Okay, yes, sir.
If it has 4 regions, why wouldn't it be tetrahedral?
Well, the electron geometry is tetrahedral. But for the polar, to determine if it's a polar molecule, all we need to worry about is the molecular geometry. And so since there's one lone pair of electrons, that means it's not, well, yeah, the electron geometry is tetrahedral, but not the molecular geometry. So if we just worry about the bonded atoms, what does this look like? A triangular-based pyramid, right? And so you have to be able to see this in your mind, what it looks like. So that looks like this. Okay? Triangular-based, but it kind of goes up into a pyramid. Okay? All right, what's our next step once we have the molecular geometry? Do the line test. Oh, not quite. Check the bonds, right? So is a hydrogen-nitrogen bond, that's all there is here. Is that a polar bond or a non-polar bond? Difference is 2.1 and 3.0, right? That is a polar bond. Good. So which side is partial negative? Nitrogen's partial negative. These guys are all partial positive. Can we separate the negatives from the positives? Here it is. Can we draw a line that separates the negatives from the positives? Yeah. Positive, negative up here, positive down here. Good? And so if we actually draw a line here, it's kind of straight, right? Okay. Positives all down at bottom, negative up top. But if we drew it like this, we can't see that, can we? So you have to have the molecular geometry. I'm just stressing that because it's easy to fall into the trap of not worrying about that step. Okay? One more? 5 more? Okay, let's do water. H2O. And after a while of doing this, you'll start drawing them as the 3D model, the molecular geometry. But until then, here's what it looks like. This is the Lewis structure. So if we were to predict whether it's polar or nonpolar, what would you say just by looking at this? Nonpolar, right? But that's why we can't do it from here, right? So what is the molecular geometry here? Bent, 4 regions and 2 lone pairs. So it's going to look like this. Okay. And this is a polar bond, partial negative, partial positive, partial positive. We can easily draw a line that separates the positives from the negatives. So that looks like this here. Pretty easily draw it, right? Okay. You'll see that? Okay. So this is a polar molecule. I forgot to write this one is also a polar molecule. Good? You want to try some on your own? Okay. Section 3. From the following molecules. Oh, that one right there. They've been drawn for you. All you have to do is tell whether they're polar or nonpolar. So it kind of gives you a baby step here, right? But just make sure you have these drawn, or look at the molecule anyway, right? So I will have these for the exam. When is the exam? A week from today. Okay. Did you say Monday?
Yeah, always the.
Okay, it says Monday probably.
Yeah, but it's-
Sorry about that. It's on Tuesday during class. Okay. It's online. All of my exams are online. Even the final. So let's go ahead and practice some of these. If you want to do some together, we can.
for this one. This is for my lab, but I was trying to figure it out. Do I do these separately? Like, how do you split them?
Remember what I said just earlier?
Yeah.
Carbon, hydrogen, this is nonpolar.
Okay.
And this carbon, that's nonpolar.
Okay.
The only part that's different from electronegativity is this bond and that bond.
Okay.
So all we have to worry about, this side right here is positive, partial positive,
Okay.
because this is nonpolar, right?
Right.
So partial positive, and the difference here is polar, right? So it's partial negative, partial positive.
Okay.
We can draw a line so that makes this. Or you're trying to
Just like what plane? Like.
So you're wondering what the geometry
Like
is?
yes.
Oh, okay,
yes.
okay.
Yeah, that part.
Okay. So let's see. This one has 1, 2, 3 regions, right?
Okay. Yeah.
This one has 1, 2, 3, 4 regions.
So you count this one in between.
Yeah.
But not like.
So if we're dealing with the central atom, if that's the central atom,
Okay.
we have tetrahedral.
Okay. Okay.
If that's the central atom, we have trigonal planar.
Okay. Okay. Sweet. Yeah, that makes sense.
Good?
Okay. Yeah, that's perfect. Sweet. Thank you.
How are we feeling? Do you want to go over any together or move on? What are you feeling? Last one? Okay, let's do it. So HOCl. All right. So what's the central atom here? And let's go ahead and count these. 1 plus 6 plus 7. That's 14 to 4, 6, 8, 10, 12, 14. Okay. So they're all good there, right? All right. What's the central atom? Oxygen. How many regions? 4. 2 lone pairs. So what does that make the shape? Bent. So it looks like this. Right? Okay. Now we have 2 different bonds. They're not the same. So we have to check each one. What's the difference? Is this a polar bond or non-polar bond? It's a polar bond. Partial negative is the oxygen or the hydrogen? Oxygen, so that makes that partial positive. What about the oxygen chlorine? Difference is 0.5. It's barely polar, right? But still, the oxygen is more electronegative. So that's what it looks like. Can we separate with a straight line the positives from the negatives? Yeah. So this is what? Polar or non-polar? Polar. Good? Does that make sense? Or did I miss some steps that you're not quite clear with? Anything else? Okay. Yeah, we'll just leave it at that. Okay, the next part on your worksheet, you have to do everything. They just give you the compound. Let's practice this. Let's see if we can do this. Do you want to do some together? How you feeling? Which ones do you want to do? You pick them. CH2F2. That one looks icky, right? CH2F2. All right. So let's count. There are 4 valence electrons for carbon, 2 for both of those hydrogens, and a total of 14 for these fluorines. You okay with that little skipping steps things type deal? You okay? Okay, so that's 20 total. Which one's the central atom? carbon, good. We have 2 hydrogens on it and 2 fluorines. Oops. 2, 4, 6, 8. We have 12 left. Put them around fluorine first. 2, 4, 6, 8, 10, 12. We used all of them. They all have octets. Good. Now what?
Determine if the bonds are polar or nonpolar.
Almost. I guess it doesn't matter if you determine if it's a polar bond or not, but we also have to determine the shape, right? I just don't want you to forget that step. That's why I have that next. So we got to know the molecular geometry, which is 4 regions. What is it? Tetrahedral. So it doesn't matter how you draw this, guys. I could draw my 2 hydrogen on that side because this thing moves around in space, right? Doesn't matter how you do it. All right. So let's check the bonds. Is carbon-hydrogen bond polar or nonpolar?
It's nonpolar.
Nonpolar because it's carbon-hydrogen bond. That's a common bond. So let's get that one down. You don't have to memorize if you don't want to. Just look it up. Okay? Just look at the values. So this part right here is nonpolar. So all we have to look at is the other side. It is a polar bond because fluorine is the most electronegative. It's partial negative. Oops, let's use a different color here. Partial negative, and partial positive over here. And we can easily separate with a line. So this is polar. So even the icky yucky ones aren't too bad. Well, there probably are icky or yuckier ones that are bad, but not in this class, okay? Or was that bad? You tell me. And if it's bad, that means we just need more practice, right? Just need more practice. You want to do another one together? Because I'm pretty good at these. How are you guys? I mean, but I'll do all of them if you want.
Can we try another one and then?
Yeah, you tell me. Which one? Which 9?
CH2O.
CH2O. I was just looking at that one. Good. Okay. How many valence electrons do we have? 12 electrons. Good. Any questions there? Which one's the central atom?
The carbon.
Carbon. Two, 4, 6. We have 6 left. Put them around oxygen. We used them all. Now what?
Determine the shape.
Make a double bond, right? Are we good? Okay. Now what?
Now we determine
The shape, the molecular geometry, right? Which is, how many regions do we have? 3. So what is it?
the shape.
Trigonal planar. Can I turn this any way which I want? Can I put the oxygen on top instead of on the side? Yeah, that's okay. It's going to look something like this, right? So we got to know what trigonal planar looks like in our mind. Okay. Which is the only bond we have to worry about? Carbon oxygen. Carbon hydrogens. And again, ladies and gents, if you don't want to memorize the carbon hydrogen thing, that's okay, don't. Just check it, right? If you want to just check it, yeah, that's fine. Okay? But the reason I say if you memorize it, there's so many carbon hydrogen bonds. in what you'll see here, okay? So if you just know that those are nonpolar, then we just have to look at that one right there. This is partial negative, partial positive. We can easily draw a line there. Good? Polar or nonpolar? Polar. Good? Any other ones you want to do together? Again, if you guys can get so good at this, you dream about it. That's where we know we got it, okay? I mean, I'm sure you don't want to dream about chemistry, but but if you dream about chemistry this semester, you'll have to take it again, right? No, I say that because when I was a kid, I played video games like it was out of style, you know, and you start dreaming that you're Mario or whatever. Okay. That was probably a little bit too much video games. Okay.
Do you think you could scrub a little bit?
Yeah.
Just so I could see that.
Yeah. Far enough.
Yeah.
Is it safe to say, like, so for bromine, like, if it's just, what do they call that, a monoatomic?
The diatomic molecule,
Yeah,
like Br2.
yeah, is it just safe to say, like, they're gonna not be polar because it's
Well,
the same thing?
Yeah. What's the bond? It's just a bromine-bromine bond. What's the difference in electronegativity? Zero. Yeah. So it's nonpolar.
Yeah,
You don't even have to look at it.
okay, I just wanna make sure that's a safe assumption.
Yes.
I'm not gonna think myself into it.
Yeah. Does it make sense though?
It does.
Why we can?
Yeah.
Okay. Good. And this isn't even the last step, guys. So we did all of that stuff, all of the Lewis structure, molecular geometry, so we could do polarity. We're doing all of that so we can do something else next. Well, if we get it down, won't be too bad. Okay. Again, if you feel like you want to do another one, let me know.
Can we do the one for, sulfur and oxygen too? The second one, SO2?
Oh, yeah. Yep, sure can. Okay, so we have 6 times 3, that's 18 electrons, good? Sulfur's the central atom. We used 4, so we have 14 left. 2, 4, 6, 8, 10, 12, 14. What do we need? Whoops. Double bond. Doesn't matter which side.
Okay.
Okay. That's the structure. Is that your hard part?
That is what I got, but it looked funky, so I wanted
Okay.
to double check.
It can look as funky as it needs, but you just have to count. Do they all have 8? Do they all have the octet? And did you use the right amount of electrons? So double check that every time, guys, because it's easy to make a mistake on counting them, right? And if you count them wrong and then draw it, chances are you're going to get everything wrong. Okay? And that's just the first step. Okay. Want to keep going? How many regions? 3 with one lone pair, so what is it? Bent. Is this a polar bond or non-polar bond?
Polar.
So sulfur, oxygen. What's sulfur again? Is that 2.5?
Yeah, correct.
Okay, so we got a difference of 1, so yeah. So partial negative down here. And you guys know what I'm drawing here. I didn't show you. This right here is a Greek letter delta. Partial positive, partial negative. If that drives you nuts, just put negative and positive. I'm okay with that. Okay? Why do I do it this way? Because this is the way that I learned and it's stuck. Okay. So can we draw a line? Yeah, so this is a polar molecule. And if, yeah,
So, you know when you say, what's the shape gonna be? Are you going based off that chart you gave us?
uh-huh,
Okay.
yep. And if you're gonna go in to do more chemistry, higher chemistry, then it's a little bit more complex than this. But let me just tell you, for the rest of you, just close your ears, okay? Okay. No. So for example, if we have, what's an example here? Sometimes we have a compound, for example, let's say SH2. Looks like this, right? And what's the bond between S and H? Polar or nonpolar? So this is 2.5, this is 2.1. Nonpolar. Oh, we don't have any polar bonds, so what are you going to say? Nonpolar, right? But because of its shape, this is a polar molecule. Just so you know, okay? For everybody else, we're just not going to go there. Okay? So, another easy thing, Elizabeth, is if you have lone pairs around the central atom, and this is for everybody really, if you have lone pairs around the central atom, it's a polar molecule. It is. Okay.
Can you do SiCl4?
Yeah, let's do it. SiCl4. Silicon has 4. Chlorine has 7 times 4, that's 28. That's a total of 32 electrons. Silicon's a central atom. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, 24, 26, 28, 30, 32. We always, all 32. Sorry, just quickly get there. What's the shape? Tetrahedral. What's the bond? Polar or nonpolar? 3.0. What's silicon? I don't know that one.
1.8.
1.8. Is it polar?
Yeah.
Yeah. Okay. So that's a polar bond. So if we draw this, silicon with chlorines looks like this. This is partial negative. Let me use a different color. Partial negative, partial negative, partial negative, partial negative, partial positive. Can we separate the positives from the negatives with a straight line? No, we cannot. So this is nonpolar. Mm-hmm. Good?
Yeah.
Great. Thanks for asking that one. Do you want to do any others before we move on? No? All right, let's move on. So we're going to use polarity for the rest of the semester. Make sure we can do that. We'll talk about that later. Okay. Okay, the next section, next topic we want to learn is intermolecular forces. Okay, if we have a water molecule, looks something like this, right? With me? Okay. If we have one, how many do we really have? Trillions of them, right? You can't just have one. So we're going to have another one. And this side is partial negative. This side's partial positive, right? We're going to have another one here. For this other water molecule, which part of the water molecule is attracted to this oxygen on the first molecule? The positive is attracted, right? So you got H like this. And so we have this is partial positive, partial negative. And we have a little bit of an attraction between these right here. This right here is called an intermolecular force, or IMF. Good? Sorry. Uh-oh. Let me start over. Okay, it's just the force, the attractive forces between molecules. So this is not a bond, but if you look at water, it's kind of held together, right? And if you drop some water on, let's say, a piece of plastic or a piece of wax paper, what do you see? It kind of speeds up, right? They kind of go together because of that intermolecular force it has. Good? And water has a pretty strong intermolecular force, and this is why, I don't know if you ever see a gerbil or a hamster get water. All they have to do is push there's a little spout coming out of the bottle, right? And they push a little bead, and then water comes out, right? But if they don't push it, the water doesn't drip, right? Because of that surface tension between so you have this little tube right here, and then you have this little ball that's in here. There's not much space right here, and this is not drawn very good, but there's not much space right here and here. And so he pushes it up. It doesn't have to push it up very far. It doesn't even have to push it up at all. It just has to touch it, and it'll come out a little bit. You can do the same thing if you get a screen, like on the windows or something, and you cut it out and stick it in a mason jar, and just put the mason jar lid over it. You put water in it, goes inside the holes, right? Upside down, and it won't fall. The water won't come out because of that surface tension. Have you ever balanced or floated a paper clip or a staple on the top of water? Yeah, because of the surface tension. It doesn't mean the paperclip isn't less dense than water, but it's because of that surface tension, which is caused from the intermolecular force. Good? All right, let's talk about the different intermolecular forces. So I'm going to start with the strongest and then go down. So strongest here, weakest down here. Weakest. So strength goes up. Strength. Okay. All right, the first one is ion-ion. And these ion-ion intermolecular forces are between, any guesses what kind of compounds? Ionic compounds. That's why they're the strongest. Why? Because they have a full positive, full negative. They have a stronger attraction. That's why when you look at salt, salt has an extremely high melting point, and that's because of the strong intermolecular force. You take sugar, looks kind of like salt, right? But it melts easily. We melt it every year for Christmas, right? For caramel, okay? So low melting point because it has a weaker intermolecular force. Good? So the ion-ion is for ionic compounds. And then going into the covalent compounds, we have hydrogen bonding. I'm going to draw that write that a little different here. Hydrogen bonding. And this is for polar covalent compounds. And I'm going to write one more thing. Only if hydrogen is directly bonded to fluorine, nitrogen, or oxygen. That's why we call it hydrogen bonding. Not because it's bonded to a hydrogen. Why is it just those three, fluorine, nitrogen, and oxygen? Because those are the highest electronegative elements. Okay? But if it's with any other element, it's not hydrogen bonding. Okay? And the hydrogen has to be directly bonded to it. Yeah?
How can you tell when it is?
When it is, we draw the Lewis structure, right? Yeah. Great, good answer. Good question. Good? Sorry, I wasn't talking to myself saying good answer, okay? Okay, sorry. And then I go and snort. Okay, here we go. Next one is dipole-dipole. And this is also for polar covalent compounds. Just the rest of them that are not hydrogen bonding.
What's your second word on that?
Oh my gosh, thank you.
Sorry.
No, I'm sorry. Polar covalent compounds. You're going to make me a better writer here. Thank you. So that's for the rest of them. Good? And the last one, the weakest, is London dispersion force. And that is for the non-polar. Covalent compounds.
Disperse.
London dispersion. So that's for all the non-polar molecules. Good? Yeah.
So this might not technically be on this scale,
Okay?
Where do van der Waal interactions fall?
What?
Van der Waal interactions?
Oh, that's all of these.
Okay,
That's for the covalent compounds,
gotcha.
not the ion-ion one. And they're all relatively weak forces, but in strength, that's how it goes. So ion-ion's probably way, way up here, right? And then way down here are the rest of them. Good question. Okay, so van der Waal forces is another name for these lower three. But you don't need that for this class, but maybe, I don't know. Good? No, thanks for asking. Are we good? I'm going to add one more thing to this. And also from bottom to top, the melting point / boiling point increases from, and does that make sense why we kind of talked about it a little bit? If it has a weak intermolecular force, it's going to melt really easily, right? At a low melting point, or it's going to boil at a low boiling point, okay? As we get higher and higher up to the ionic compounds, well, it's going to be really hard to get those things to be broken apart. Good? So a hydrogen bonding is a type of dipole-dipole force, but we have its own category because it occurs in the human body a lot. And so, anyway, good? All right, let's see. We'll take a little break. Let's see. Let's do section 5 real quick. Try that, and then I'll come back if you have any questions. We can go at the end.
I have no idea.
right, any questions on section 5? Should we go over the answers? Okay, on the top row from left to right, ion, ion, London dispersion, ion, ion, dipole, 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 dipole. Next row, London dispersion, dipole, dipole, London dispersion, hydrogen bond, dipole, dipole. Questions? Did you get them all right?
So we're going based off of our. Yes,
So that, yeah, we have to, so to do this, well, should we make some steps on how to determine this, guys? All right, sorry about that, I didn't. Okay, here we go. Let's see. Determining intermolecular force. You guys okay if I just say IMF? Okay. Step 1. Determine what kind of compound is. If it's ionic versus covalent, we know if it's ion-ion or one of the other 3, right? Determine if the compound is ionic versus covalent. Step 2. And if it's ionic, it's ion-ion. So we're done with that one, right? For all of the covalent compounds, we have to determine if covalent compound is polar or not. If it's not polar, what is it?
Non-polar.
Yes, if it's nonpolar, it's nonpolar. Sorry. If it's nonpolar, what intermolecular force is it?
London dispersion.
London dispersion, sorry. If it's polar, then it's either hydrogen bonding or dipole-dipole, right? So the next thing is hydrogen bonded to fluorine, nitrogen, or oxygen. If it is, then it's hydrogen bonding. If it's not, then it's dipole-dipole. Good? So if you want an extensive list, then you would say determine the Lewis structure, determine the molecular geometry, right? All that stuff is included in determine if the compound is polar or not. Good? Okay. All right, ready to move on? Or do you have questions? Do you want to try some of those together? We can. You just let me know.
Well, with the, like HCN,
Mhm.
would that be hydrogen cyanide?
HCN, yeah, or cyanic acid is what the real name is. But yeah,
Right. So, wouldn't that be an ionic compound though? Or does it have to be,
kind of is. Yeah, I guess so. Yeah, it is.
so, I know you said.
So it's ion-ion.
It's ion-ion?
Yeah.
Okay, and then,
I'll have to double check on those ones. I think it is because acids are salts before they are in a solution. And now, what makes an acid, we'll get there, if the salt is dissolved in the solution. And it's not just any salt, but it's salts with hydrogen and something else.
Okay.
So, yeah, I believe it's ion. Whoops, my bad. Good? Will I trick you like that? I hope not. If I do, catch me on it. I'm on your side. I didn't write this test. Okay? Anything else? Great question. All right. Now let's put these next compounds in order of lowest to highest melting point, for example. Lowest to highest. So order from lowest to highest. Melting point. Okay, so you'll have to know how to do this for the exam. Okay. So we got CCl4, CBr4, and CH4.
Are you on number 6?
No, this is just the next thing in the notes.
Oh, okay.
Okay? So how do you tell which one has the highest or lowest melting point? The strength of the intermolecular force, right? Like I had up here, as the strength increases, so does the melting point, right? And boiling point. Okay? So we got to determine what kind of intermolecular forces these are. Can we do it? What about CCl4? Any guesses before you actually draw it? Okay. Then draw it. After you get to do these and do these and do these, you could just see what it is. It's like the Matrix, right? I'm just kidding. Is that too old of a show for this group? Okay. Talk like that to my high school kids and they say, what? Okay. Or do you want to do these together? Oh, okay, sorry. Let's go. So, is this a polar or non-polar molecule? Non-polar, because if we draw it, it'll look something like this, right? Whether this is a polar or non-polar bonds, you can't draw a line that separates them because they're all the same, right? Okay, so this is non-polar. So what's the intermolecular force? London dispersion. Okay. What about this one and this one? They all look the same, don't they? They're all tetrahedral with the same elements bonded, So they're all London dispersion. Do you get that, or should we draw them? What? Get it? Should we do it?
No, I'm saying like, I can see it.
Okay.
We're asking, yeah.
Because it's carbon, they're all carbon in the center. So you really have to look, is carbon chlorine a polar bond? It is. What about carbon bromine? What's bromine? What's the electronegativity value? What is it?
2.8.
2.8? So it's nonpolar anyway, right? And that's nonpolar. So these are both nonpolar molecules. So London dispersion, London dispersion. Great. Now which one's higher in melting point? They're all London dispersion. Now we got to check something else. Okay? And this is new. If they all have the same intermolecular force, we have to check their mass, their molecular weight. Do you guys, did I teach you how to do that? Okay. Molar weight, molar mass is the atomic mass. We talked about atomic mass, right? The atomic mass is added up for each element in a compound. Okay, so if we do that, carbon has a molar mass of what? Or atomic mass of what? 12. And it's really 12.01, but are we okay with just saying 12? Okay. If you have to round a lot, like up to half a unit, then don't round, okay? Or if you're ever unsure if you should round, then don't round. Chlorine
34?
is 35.5 maybe. We can round it to 5. And there's 4 of those. So it looks like we're doing the same thing what we're doing for counting the valence electrons, right? Just make sure you know it's not the valence electrons, right? Okay. So 35.5 times 4, someone with the calculator, someone
142.
for all of it?
No.
And then plus 12?
154.
154, and that's grams per mole. We'll get there, don't worry about that so much. Okay? So that's the molar weight, molecular weight of that compound. Let's do it for this one. What's the molar mass of, or the atomic mass of bromine?
70?
70. It's a lot bigger than this, and there's 4 of them, right?
Wait, bromine is 79.9.
Yeah, so close to 80.
Yeah.
So 80 times 4 is 320,
Yeah.
plus 12, 332. Is everybody following me what I'm doing?
Yeah.
Or you lost? Anybody lost? Please tell me. Okay, so I'm just getting these values from the periodic table, the bottom number on the periodic table. Okay, so this one is carbon is 12, hydrogen is 1 times 4, that's 4, that's a total of 16. Okay, so if we're putting this in order of lowest to highest, which one's the lowest? CH4 has the lowest, and these are just prediction, guys, the lowest melting point. Then CCl4, then CBr4. So think about it like this. And it's not exactly like this. This is a good analogy. You have a pan of water on the boil and a pot of water on the boil. Which one's going to boil first?
The pan.
The little pan, right? Because that has less mass, right? So, not exactly, but okay. Good analogy. So that's what you do if they have the same intermolecular force. You have to check their weights. Good? Should we do some on the worksheet? So on section 6 on the back, I'll do one and you do the other one. Which one do you want me to do? Yeah, which one? Oh, B, okay. All right, here we go. So we got H2O, and we're doing the same thing, lowest to highest. In this case, it says boiling point. Doesn't matter if it says boiling point or melting point. You do the same way, right? So water with this other compound, whatever it is. And we got CH4, and we got C2H6. Okay. We just did this one. Is this one, what kind of intermolecular force is this one? Or did we do it?
Yeah.
Yeah, hydrogen bonding, because hydrogen is directly bonded to oxygen. It's a polar molecule, right? So hydrogen bonding. What about this one right here? Do you see how it's written the way that it is? Instead of saying something like C2H46O2. Do you see how that's the chemical formula for this? Why did we write it like that? Because this is organic chemistry, and we don't expect you to know what it looks like yet. Elizabeth, not yet. Okay. Sorry. So we write it so the way that it's structured. So here we can see hydrogen is bonded to an oxygen directly. So what's this one? Hydrogen bonding. You with me? Okay. And what about this one? We just did that one. London dispersion. What about this one? Ugh. That one looks icky. How do you know it's London dispersion? Carbon, hydrogen compounds. That's it. There's nothing else. So that's London dispersion. It's a nonpolar because of that, right? And that's why it's going to be to your advantage that you know that. Then you don't have to draw the structure at all. That one looks icky, right? It's not really bad, but it's more organic chemistry still. Okay, so we got 2 London dispersion, 2 hydrogen bonding. So which one's the lowest? London dispersion, hydrogen bonding.
London dispersion.
Okay, so now we got to compare those two and compare those two, right? But how do we do that? With their molecular weights, right? Molecular mass, molar mass. Okay, so this one we figured was 16. We just did that one, right? This one right here was 2 hydrogens. Oh, can you see which one's less already without doing the math, guys? This has 2 carbons. This has 6 hydrogens. 1 carbon, 4 hydrogens. So CH4 is the lowest, and C2H6. Did anybody not get what I just said? Okay? I'm just trying to go through quicker. You don't have to. You can actually find the molar mass of this, and whatever one's the lowest, that's it. Okay? So C2H6, C2, that's 12 plus 12, that's 24, 24 plus 6, that's 30. So we can see the CH4 is lower than the C2H6. Good? Okay? Now we got to see which one's the lowest out of here. Can you do that without calculating, guys? Yeah, we can easily see this one's a bit more, right? So it's water, and then it's the yucky compound right there. Yeah.
I need you to explain to me how it's C2H6O2. How'd you get that from that big?
C2H6.
Yeah, how'd you get that from that big gross one?
Organic chemistry.
Oh, you mean this right here?
Yeah.
Yeah, you don't have to do that in this class. If you're going to take organic chemistry, you'll learn it there.
So like on our homework and exam?
It'll give it to you this way,
Oh, okay.
if it's on there, the way that it's structured. Because you won't know how to structure this by looking at that, right?
So
Like,
you just gave it to us?
yeah.
Or is that- Okay.
And
I
I
thought you somehow pulled those out of there.
nope, it's on part B.
Okay.
I don't know if I could do that right now. It's been a long time since I did an OChem, but
Okay, thank you.
we good? All right. I don't want to push you. We still have one more day. Should we, because we can do more review on that day. And what I'm thinking is I'll send you a study guide. I didn't send you a study guide on exam 1. Sorry. There isn't a study guide on Canvas, but I made my own study guide, and I just spaced it. So I will email you guys a study guide. Sound good?
Yes.
And, well, should I tell you how I made it?
Yeah.
Open up the exam, says, number 1, you need to know this. I don't have a question. It doesn't say give you a problem. I'm just saying what concept you need to know for that. You don't want, that's too easy. I probably shouldn't do that, right?
No.
Okay. You guys are laughing and say, oh my gosh, is this guy nuts? Okay. Are we good? All right. So I will send that to you. So hopefully it'll help, but you still have to do work. You still have to study and come with questions next time. Okay? So we have 15 minutes left. Are you burned out, or do you want to? Your call, because we have another time. So be done? Okay. We'll call it good tonight. What? I didn't hear you.
She's saying it was a lot today.
Oh, it was a lot. Yeah. It was. Probably it would have been enough to just do polarity. Go and practice this. Yeah, it was quite a bit. Uh-huh. Yeah, 3 by 5. Just the smaller ones, not the big. Okay. But in all reality, guys, if you need more than that, you need to study more. You really do. Okay? I'm going to send that to you right now before I forget.